Hello, everybody. My name is Dawson Tong, and today I will be presenting on the origins of time-dependent aluminum springback. This is a project I've been working on for the research symposium for about a year now. I've been working on it with Kessler Clark, who's in the MME department, as well as with David Anderson, who works with Novellus, which is an aluminum company, and they've been the main providers of our material that we've been looking into. So just going into a quick overview of what I've been doing recently and just the overall project. So we've been mainly looking into some issues with aluminum sheets, which experience something known as time-dependent stringback after forming. This kind of results in some unpredictable final dimensions, which could cause a company to want to scrap the part or have to reform it themselves. The main objective of this project was to be able to measure the time-dependent springback after stretch bending or draw bend testing, as well as just a better understanding of what might be causing this. The overall benefit to that is just coming up with other ways that we could possibly limit the amount of springback that occurs in these specimens. Kind of just some recent developments in the project. We've been mainly looking into some experimental procedures and trying to nail those down so we can move further into characterizing what is going on. Just some kind of metrics overall of what this project has been and where we're going moving forward. So the literature review is pretty much complete. We've acquired all the materials necessary for this project. We have not started looking into stretch bending too much and mainly been focusing on the draw bend testing. That's about 40% complete, and the next step after that is more looking into characterizing what is happening, whether it's on the micro or macro scale. Going more into some of the industrial relevance of this project and why Novellus was sponsoring it. So some of the benefits overall is just better dimensional control of those parts, as well as less wasted material and time. We could also get much higher quality parts, mainly due to that dimensional control again, as well as hopefully increasing the use of aluminum in the automobile industry specifically. Kind of some results too would be creating different forming techniques, as well as possibly looking into utilizing these techniques we find with other metals to see if they have the same mechanisms occurring in them to have that type of springback. Also too, that the aluminum industry is looking for ways to obviously penetrate other markets. And if you have a part that is not able to hold its shape correctly, that can be a pretty large issue down the road. Going into some more detail of kind of what the draw bend test is and just some articles we've been looking into. So this paper does a very good job of showing basically what the final part looks like after being tested. Let me get my laser pointer out real quick. So here is just a piece of aluminum sheet, and there's a die right here that is not obviously shown, but the sheet is bent around that initially at a 90-degree angle, and then a load is applied to it in the vertical direction as well as in the horizontal direction, and it is drawn over that die. And the resulting geometry is this bent shape. And over time, we see that the here's the initial shape, and over time, the springback begins to occur, and slowly we see it get to this point, which is a pretty large difference from the beginning. The interesting thing with this paper is that they were able to see springback occurring up to 7 years later. The main area, though, that it occurred was within the first 20 days, and this is all at room temperature. They initially kind of concluded that the springback was residual stress-driven creep over a longer period of time, with anelasticity contributing to the initial response 1 to 2 hours after the unloading. They did not really back up this paper with any conclusive evidence on what really was happening on the micro scale, but kind of gave a macro scale answer. So going into another paper, this is a more micro mechanism analysis of what could be going on. These lines here are depicted are depictions of dislocations within the material, And so as you increase your load, these dislocations in the material begin to move and interact with each other and become interwoven. And as you prolong that load, more and more dislocations move and they start to become pinned in certain locations due to those other dislocation interactions. But upon load release, some of those dislocations actually go back to their initial positions, which is noted as anelasticity. And over time, some of those initial dislocations that we thought might have been completely pinned were actually not completely pinned and also show anelastic recovery, which might be the reason behind Springback. So kind of going into what we're capable here at CSM and what we've been utilizing is mainly this draw bend test frame that I kind of described earlier. So we have 2 grips and a sample that is loaded over a roller or a die. So as you can see here, there's the initial start position of the grips. And as it is pulled, it finishes here. And this one starts here and finishes here. So the top die is in a load control, so it's at a constant back force, while the vertical grip is controlled in displacement. So it has a certain ramp rate that'll go down and pull the material over the die. We also have stretch forming, which is depicted down here. You take a piece of material and clamp it between 2 dies and then have a ram or a punch that pushes up the material. This is something that we're looking to do further down the road. We also have basic tensile testing, which is helpful for looking into anelastic behavior. Here's actually a video of the testing in progress. So as you can see, the top actuator is up here and the material is just drawn over this die as it is pulled over by that bottom actuator. So here we see a top view of the horizontal actuator, and this is at a much slower ramp rate, so we can see it slowly moving forward, controlling that back force on the material. So the material we've mainly been looking into is 6061 and 5182 aluminum. That's what we've been doing for the draw bend testing. These have all been at some varying thicknesses, just to kind of see what the material response is overall. We've also received some more material for stretch bend testing, which is mainly 5182 and some other various alloys, both in transverse and the longitudinal rolling directions, just to test and see if there's any different mechanical properties or differences in that springback or stretch bending for those alloys. So kind of going into what we've been doing with testing parameters, a key factor is alignment, ensuring that those 2 grips are in line with each other so that when the material is drawn that it's not angled at all. So that is mainly done with bubble level or by hand, because both of the grips are able to rotate freely. We've also been using a 500 back force on the horizontal actuator, as well as a displacement of 1 inch down for the vertical actuator. This has mainly been done at a 0.05 inch per second ramp rate. Some interesting stuff we've kind of been looking into is varying that ramp rate and seeing if there is any effect. Some interesting stuff though is that even at the same ramp rate, we've got some pretty different results. So these 2 specimens here were both done at 1 inch per second, and you can see that there's a pretty significant difference in the bend from one to the other. The one on the left is a lot sharper bend versus this is much more still close to that 90-degree angle. And we're not 100% sure as to why this is occurring. It could be mainly due to alignment issues as well as also lubrication on the die and also on the material. So these are kind of our initial results that we've seen. These specimens were initially done on this black line, and that is seen in all of these. versus the green line is 1 week later after that initial test. So these two on the right were both done at a ramp rate of 0.05 inches per second and show that they're fairly consistent in the amount that we're getting versus in the 1 inch per second. Again, we're having pretty different amounts of springback as well as, again, that curve. And again, this is for aluminum specifically. The ramp rate should have a fairly minimal effect given the type of material it is. And so there should not be much variation in the amount of springback we see. But if that is the case, then we could be looking into a fairly interesting mechanism behind why we're seeing springback. Also, as far as upcoming work, we're hoping to do some better pictures and have a better method of characterizing the amount of springback using a software such as ImageJ, which will be very helpful in understanding how big of a difference we are seeing in the springback from different ramp rates, and also looking into different lubrication methods to ensure that we're not affecting the amount of force that's being applied to the material because of that. Just some upcoming challenges and opportunities that I've had throughout the semester has mainly been labability due to COVID and also just overall time restrictions. Also, although we've done a decent amount of tests, we're not 100% certain on our parameters and also testing procedures because they need to be fairly consistent in order to produce repeatable tests on the material, so then we can actually start to characterize the springback and really put something what's going on. I just want to say thank you. My name again is Dawson Tong. Here's my email. If you have any questions, just reach out to me. And here's just a slide for references. Thank you again for this opportunity to share my research and also for the funding for this project. And have a good rest of your day.